Okay, so this begins the final video for chapter on combustion turbines. We went ahead and looked at the basic Brayton cycle process, which is a representation cycle of a combustion turbine using air as the working fluid. We went through the isentropic efficiencies and how to handle those for the compressor and the turbine. So now let's bring it all together. We'll do an example problem, and then I'll go and look through some variations to this cycle and also some specific examples of different commercially available turbines. So let's look at an example problem. Again, this is taken from your book, and it says that a combustion turbine possesses the following characteristics. So we have here a compressor, and the compressor takes in air at 97 kilopascals at 30 degrees C, has a pressure ratio of 5.5 and efficiency of 84%. So that air coming out of the compressor goes into a combustion turbine. The pressure through the combustion turbine, it loses pressure of about 3%, and the air coming out of the combustion turbine, the combustion chamber, is 1,000 degrees Celsius. That in turn goes into a turbine where the air coming out of the turbine is at 100 kPa, excuse me, and the efficiency is 88%. And then we have a generator efficiency of 98%, which is turned by the turbine. So basically what this problem is doing, I'm not going to go through all of the details. I believe at this point you guys can kind of take what we reviewed and combine it all into a full analysis, but I just wanted to go ahead and, based on this defined cycle, I want to at least develop the overall thermal efficiency, right? So we're going to end up doing and limiting to, at least in the context of this video, is trying to bring all that together in terms of computing the overall cycle thermal efficiency, right? We're not going to do heat rate together, and we'll look briefly at a TS diagram for this particular cycle. So we're going to look at the overall efficiency. Again, the overall efficiency for any heat engine is basically going to be the net work that you get out of it divided by the heat rate in, right? And efficiency is basically what you want over what you have to put in, right? So what you want from any kind of heat engine, including a combustion turbine, is the net work. What is the net work coming out of the system, out of the combustion turbine process, and what's actually going to the generator, divided by what do you have to put in. What you have to put in is the amount of heat going into the combustion chamber. So if we're going to go ahead and do net work, well, we can kind of take the net work and we can say the net work is going to be the turbine work minus the work that the turbine uses to turn the compressor, that divided by the heat in. So if we were to go ahead and do that, we would factor out the CP for the turbine, right? The turbine CP will be higher than the compressor CP since the temperatures are significantly different. So we have here temperature going into the turbine minus the actual temperature coming out of the turbine. Then we subtract out the compressor work, which again, if we factor out CP, we'll assume the CPs to be constant across the process, but not constant across the cycle, right? Since the CPs are going to be much higher, the temperatures are much higher in the turbine than they are in the compressor, we'll just go ahead and factor out the CP for each process. But then again, the CP through the compressor and the turbine are different. Anyway, if we were to continue this, we would find that the CP, the work for the compressor would be the, again, CP delta T. So I was about to put T1, but it's actually going to be T2 actual coming out of the compressor minus T1 going in. All that divided by the heat in, which would be the, factor out CP going into the combustion chamber, multiply the temperature difference, which would be the temperature coming out of the combustion chamber, minus the temperature going into the combustion chamber, which is the actual temperature coming out of the compressor. This process, that basically is how the total thermal efficiency would be. Again, I'm not going to go through the full analysis in this video. It's something that at this point I think you guys can do on your own. But I did want to kind of just point out how those temperatures are affected, right? So these temperatures, if you were to replace those with isentropic temperatures, which would be the isentropic, if we were to assume that the compressor and the turbine work in an isentropic process, these temperatures would change and result in the efficiency of the cycle going up. But as the isentropic efficiencies of the compressor and the turbine go down, that changes the temperatures coming out of each of those processes in such a way that it actually decreases the overall efficiency of the cycle. To the point that for this particular cycle, if you were to calculate the efficiency and go through all the numbers, you would find that this particular process cycle operates at a 25.6% efficiency. And you can see on, this is a TS diagram for this particular cycle. Again, we have these constant pressure lines. You can see the pressure going into the compressor, non-isentropic compression up to 0.2 coming out of the compressor. Then that goes into the combustion chamber, but there's a 3% drop in pressure. So that's coming out of the compression chamber. Then we have an expansion through the turbine, again, where the temperature where the process is non-isentropic, so we have some entropy production during that. Coming out at T4, that's rejected to the atmosphere. Then we have T1 coming in, which is being taken in from the atmosphere. So again, that's the basic analysis of what I would call a simple Brayton cycle or a simple combustion turbine. But there are variations to these that help kind of increase the efficiency without necessarily needing to add more energy across a system boundary. Let me show you what I mean. I'm going to go ahead on this slide and I'm going to go ahead and draw out a simple Brayton cycle. So again, we have a compressor, we have a combustion chamber, it's basically just a heat exchanger. So we have a combustion chamber, which is a Q-in process, compressor, which is a work-in process, a turbine, which is a work-out process, and here again, if we have a heat exchanger, if we go ahead and do the Brayton cycle approximation for a Q-out process, and here's a cycle, right? So here is our Brayton cycle. State 1 goes into the compressor, state 2 out of the compressor, state 3 out of the combustion chamber or out of the heat, then into the turbine, and then out of the turbine into the heat rejection process and back to state 1. And then if we draw a system boundary around the whole cycle, you can see that the energy crossing the boundary is Q in, Q out, work in, and work out. So this efficiency, thermal efficiency, again, as we looked at earlier, is the net work divided by the Q in. Now, we can actually vary this cycle slightly to increase the efficiency without actually trying to generate another energy term that crosses the boundary. Now, let's explain what I mean. The temperature coming out of the turbine is greater than the temperature coming out of the compressor, right? Now, if I can somehow increase T2 before it goes into the combustion chamber, that allows me to decrease the amount of heat needed from the combustion chamber. And if I do that, if I decrease Q in, well, that increases the efficiency. Right? So how do I do that? Well, there's a few ways. There's a few reasons why that would be important. The thing is, with the combustion chamber, it runs on fuel, right? You're burning a fuel. So fuel prices overall have continued to escalate, right? And
increase. And as the electrical system or the utility grid becomes more stressed, more thermally efficient turbines are becoming, right, increasingly attractive. So there are many variations of basic combustion turbine cycles, but two adaptations are important. One is definitely using what I would call a regenerator. What's neat about a regenerator is that the regenerator, it has an ability to take this temperature, the heat coming out of the high temperature air coming out of the turbine, can be used to preheat the air coming out of the compressor before it goes into the combustion chamber, decreasing QN, increasing efficiency, and decreasing the amount of fuel needed to generate that the work out. In another addition, another variation, which is different, is something called an intercooler. Now, instead of, for example, taking this work in right to the compressor and increasing from P1 to P2, what I can do is that I can break up that compressor process. So again, instead of having P2 over P1 as a compression ratio, I can actually split this into a two process. So I can have some sort of intermediate pressure where I have two different amounts of work going into the compressor, where when I hit pressure, some intermediate pressure, I actually take away heat from the air. So I take away energy from the air in the form of heat in order to decrease the temperature of the air. And then I finish the rest of the compression process, because it takes less work to compress cool air than it does to compress hot air. So if I break up the compressor into various compression stages and then decreasing the temperature coming out of each compression stage, I can actually overall, when I add up all those stages, it would actually be less work than it would be in doing it as a one-stage process. And so as again, net work is work of the turbine minus the work of the compressor. If I can make the work of the compressor less, I make my net work higher, which makes my efficiency higher. So what the diagrams would look like something like this. So with the regenerator, what I would do is that I would have the air coming out of the turbine, the exhaust gas, exchange heat to preheat the air coming out of the compressor, so that that air exchanges heat. Then I would reject the turbine air, and then after the heat is exchanged to the compressed air, then the compressed air would go into the combustion chamber, reducing my QN. And if I take that regenerator process and I combine it with a intercooler, right? Again, if I take my compressor here and I split it up into two stages, so I take air in, I compress it to some intermediate pressure, right? So again, maybe that's P1 and this is some PX coming out. I reject the heat coming out, so that now the temperature going into the second stage compressor is the same as the temperature coming in from the inlet air, but the pressure is higher. And then I come out at some P2. The amount of total work for the compressor is less than a one-stage compression process. Right, so again, two things, a regenerator and intercooling, both done to increase my thermal efficiency, which would be the net work or turbine work minus compressor work over QN. The regenerator decreases QN. The intercooler decreases the compressor work, which basically results in an overall increase in my efficiency. So those are just some interesting ways to increase gas turbine efficiency, which basically decreases fuel consumption. At this point, I'm just going to briefly go over examples of commercially available turbines. I'm not going to go into a lot of detail. These are detailed in your book, of course. I expect you guys to be reading the chapters as much as you do watching these videos. So, okay, looking at the examples here, combustion turbines they are commercially available for electrical power output in a range from 30 kilowatts upwards of 250 megawatts. So the term microturbine is applied to combustion turbines with electrical outputs between 60 and 100 kilowatts. And industrial turbines typically outputs of a half a megawatt up to 250 megawatts. There's a company called Solar Turbines, right? Solar Turbines Incorporated. They manufacture a line of combustion turbines that have electrical outputs between 1 and 15 megawatts. So again, they kind of give you a chart here where they have a family of combustion turbines with the names and their nominal output and heat rate. And you can tell that the heat rate decreases with increasing output. Here's an example of one of solar turbine. It's a solar turbine Mars 90. It shows that basically on this graph that at an inlet temperature, as the inlet temperature increases from 59 degrees to 113 degrees, the output decreases from close to 10 megawatts down to about 7 megawatts, right? So that's a decrease of nearly 27% of power as the inlet air increases in temperature. Again, due to the fact that it costs more energy to compress higher temperature air than lower temperature air. General Electric also is a major provider of different energy systems in the US. So there's more than 9,700 GE Energy gas turbines have been installed worldwide. The company offers basically two different lines of combustion turbines. You got heavy duty ones and another one that's called aeroderivative, which is based on a line of aircraft engines. So the heavy duty gas turbines are available with electrical power outputs from 26 megawatts up to 480 megawatts. Those are basically used for utility and industrial applications. Here's a basic cutaway drawing of an aeroderivative. Again, it resembles much of an airplane gas turbine. Again, some performance data. As the ambient air increases, you can see that the output decreases. The power output decreases. Here's a cutaway drawing of another aeroderivative gas turbine. You have the intercooler here, like we talked about earlier. You have here the low pressure compressor, the high pressure compressor. And again, it resembles that of a turbine used for aircraft propulsion. Here's some performance data. Again, various different types of models along with their heat rate and base energy rating, output rating, and efficiencies and mass flows and such. Again, the rest of these are just, again, other examples. Here's something called a capstone turbine. They manufacture on a lower power end, 30 kilowatts to 200 kilowatts, and they are known as one of the best microturbine manufacturers in the US. Here's their basic characteristics. Again, 30 kilowatt power output with a 13,000 BTU per kilowatt hour heat rate. Efficiency around 26% with an exhaust temperature of 530 Fahrenheit. You can kind of see here the power output and efficiency as a function of inlet air temperature, right? So again, as the inlet temperature increases, you have a decrease in power output as well as net efficiency.